You need to know about what are called the exponential decay curves for a capacitor. Well, what are these? Well, these are really just talking about how the charge and other quantities vary on a capacitor as it's discharging, as the charge is flowing off. To show what I mean, let's look at a circuit involving a capacitor which has already been charged up. So we've already had a power supply, and we've already moved electrons from one plate to the other. So we've created a positive charge on one plate, plus Q, and a negative charge on the other plate. Well, if I now discharge that, that means allow the charge to kind of go back to where it was originally. Then I needed to connect a circuit between the plates so that the electrons can flow. At the moment, there's just air surrounding here, so there's no way for the electrons to, that's an insulator, so they can't move back. But if I connect this circuit, then obviously they'll flow. Well, how is that going to happen? What's it going to look like as time varies? In other words, what I'm saying is, if I had a graph of the charge on each plate, the magnitude of the charge on each plate against time, what would the and I turn on the switch at time equals 0. So if I connect this switch here, bang, at t equals 0, then what's that graph going to look like where Q is the charge on the plates? Okay, well, it's going to start at some kind of initial value, and let's call that Q0 because the 0 means time 0, so it's the charge at time equals 0. And then let's try and figure out what it's going to look like. And it's obviously going to go down because the charge is going to rebalance. Hopefully it kind of makes sense that initially it's going to flow off really, really fast, because initially we've got like tons of electrons on here and a real massive absence of electrons on this plate. So initially they're going to feel a massive repulsion from each other, so as soon as the circuit is connected, they're just going to fly off as fast as they can. So there's going to be a really big rate of change of charge at the beginning because there's more charge. In fact, it turns out that it's true to say that the rate of change of charge, or delta Q by delta T, is actually proportional to how much charge there is at any one time, which kind of makes sense, yeah? So we're going to say, okay, well, initially it's going to be really sort of fast change, but obviously as more electrons come off, then we're leaving, there's not that much repulsion going on. So gradually, the gradient's going to get less and less. There's going to be a slower rate of change. And yes, you've guessed it, it's going to be an exponential shape because it's going to be a nice smooth curve. So let's draw it on. So roughly speaking, we're going to have a nice exponential shape. Remember, an exponential will never reach the x-axis. Or they might be new to you, in which case we're going to look at the maths of exponentials very shortly. So what about the other quantities of the circuit? What about the potential difference across the capacitor? Let's do a graph for that. Well, so what we're saying this time is, how is the potential difference between the plates going to vary over time? Well, we could actually measure that. We could actually do an experiment. We could connect a voltmeter between the two plates any way you like. Somewhere like that would do fine. And then over time, we could start taking readings at the moment that the timer starts. So at time equals 0 is when we close the switch. Well, similar to the charge, it's going to start at a maximum value, which we could call V0. And we know that that is going to go down to 0 by the time all the charge is kind of redistributed and gone back to where it was at the beginning. And well, it's going to have a very similar shape. We actually know that because remember that Q equals VC. So Q and V are proportional. Q is proportional to V, so the graphs are going to have the same shape. At any one moment, the voltage is going to be proportional to the charge. So there we go. So we could actually calculate the graph from the charge graph just by dividing the charge by C. Anyway, the shape of the graph then is going to look very similar. It's going to be a nice exponential shape going down and down in exactly the same way. And finally, let's look at the current. what will be the current doing in the circuit? Well, I could also do an experiment for this, because I could use an ammeter, and it's not so easy to do it for charge, because, but there are such things as Coulomb meters, but they're a bit complicated to use. So here's a graph of current against time, and we're going to do exactly the same. We're going to start monitoring the current as soon as we close the switch. And yes, we could put an ammeter here, why not? And we could measure it every 10 seconds or whatever, and we could actually do an experiment. You might have done that experiment. Okay, well, the same thing. The current is going to start really big. But of course, this time now we know that there's a relationship between current and voltage. And we know V equals I times R. So we can also use that knowledge. We can say, V equals I times R, to notice that voltage and current are going to be proportional. So as the voltage drops, well, we know that when there's less voltage, the current's smaller, if the resistance remains the same, which it is. So that's going to look the same as well. So finally, we get the final curve for current, which is going to be the same again. Down it goes, exactly the same shape. Good. So look at that, really nice and easy to remember. The Q graph, the V graph, and the I graph, the charge, the voltage, the potential difference, and the current, all have this exponential shape, and they all go in exactly the same way. Well, we better write down the equation then for these three graphs, the equations for these three graphs, and they're also very similar. Well, I'm going to write them down. We know they're exponentials. I'm going to make an optional extra video of how to derive the equations of the graphs in case you're interested to watch that. It basically comes from this idea that the charge at any one time is going to be proportional to the rate of change of charge at any one time. And from there you can derive the fact that it's exponential. So have a look at that if you're interested. Otherwise, you can just take it as read. So here we go. I'll write the equations up. So the charge varies so that the charge at time t, some people write a little t there, but I'm not going to. The charge at time t is equal to the initial charge, the charge at time 0, times e to the minus t over rc. The voltage graph is exactly the same. The voltage at time t is equal to the initial voltage times e to the minus t over rc. R and C, of course, are the resistance and capacitance of the resistor and the capacitor in the circuit. And finally, the graph for the current. Well, that's the same again. The current at any particular time is the initial current times e to the minus t over rc. So, three very similar equations for three different quantities in a circuit which shows the discharge of a capacitor. So this is for the discharge of a capacitor. Later we'll look at what happens when you're charging up a capacitor, and we're going to also deal with all the mathematics of using these exponentials. So if at this stage you're thinking, what's going on here? Don't worry, that's all coming up pretty soon.